Hi students, welcome back for the video lecturing. In this video I am going to deal the new chapter called optical fiber, which is in third module. In the third module we have the two chapters. The first chapter is Maxwell's equation and the second chapter is optical fibers. In this particular chapter I am going to discuss the basic principles of optical fiber, and upon that what are the conditions which are required to carry the light through an optical fibers. The first, in order to understand the optical fibers, first we have to know what is an optical fibers. The first prime question which is arises in your mind: the optical fibers are a thin strands of dielectric medium. So the definition will be like this: optical fibers are the light guides and they are designed to carry the light signals containing the information from one point to another point in optical fiber communication. They are specially designed transparent dielectric medium. They can carry the light from one point to another point through an optical fiber. The light specially which contains the information. For example, if a telephone user who are using the landline, he can send the voice information that will be converted into an optical rays. They are called as optical signals that will be sent through an optical fiber, and the optical fiber which carries the light, and it can reach us to another point, and another telephone user who can access the information from the optical fiber. So what they are basically a thin strand of transparent dielectric medium containing the concentric regions of refractive index material, which contains the two main regions: the first region called as a core and the second region called as a cladding. In the next slide we will discuss what is the fiber and what are the parts. What is the cross section of a fiber? I have already quoted. It consists of two main regions, that is called as core and cladding, and another region which is oftenly used to protect the fiber called as sheath or protective layer, which is an outermost layer. You can see this is a cross sectional view. It consists of three regions of three concentric regions. A centralmost region called as a core, whose refractive index is represented by N1. N1 is the refractive index of the core, and another region which is surrounded called as cladding. The core is surrounded by the cladding, whose refractive index is N2, and once again the cladding is surrounded by sheath called as polyurethane jacket, which is called as protective sheet. It is something like the insulation material exists on the electrical wire, something like that, which is an insulating material which is covered by the fiber. Fiber mainly consists of two regions, one is core and cladding, and the fiber is covered by the protective layer called as sheath. In this case, the core and cladding are the transparent regions, but whose refractive index is slightly different. The core is a centralmost region whose refractive index is N1. It is little bit higher than the refractive index of cladding. Cladding is a surrounding transparent region. The core is surrounded by the cladding, so whose refractive index is N2. N2 is slightly lower than N1. Such type of configuration which is used. Core and cladding are the transparent regions. Core is a transparent region, a glassy material, and cladding is a transparent region. But the difference we can identify in the refractive index. The core refractive index is N1 and cladding refractive index is N2. So N1 is slightly greater than N2. And thus and another region which is called as sheath. Sheath is protecting layer. So next is a vertical cross section view, that is jacket. Jacket means polyurethane jacket, and cladding and core, centralmost regions. These are the different regions we can identify in the fibers. And what will be the role of the fiber different regions in the fiber communication? The roles are different. The first thing is, what is the role of core, cladding and sheath in a fiber? The first is core. Core is higher refractive index region, and the main role of core is which guides the light and which provides the path. So the in the fiber we have the three regions, but the light can carried by the fiber through core only. The light is passes through the core region. However, the refractive index of core is more than that of cladding. So even though the denser medium which can carry the light. Next is, what is the role of cladding? Cladding is which guards the fiber, and cladding will guard the TIR. TIR means total internal reflection. So even whenever the core which carries the light means that can be leakages. The avoiding of leakage can be done by the cladding. Cladding can protect the fiber and which prevents the leakage of light from the fiber. So something like the pipe. The pipe which carries the fluid, that fluid is protected by the shielding material, something like that. The role of cladding is guarding of the prevention of light leakages. So next is the sheath. Sheath is providing the fiber by protection. The protection of fiber through the sheath or jacket, and which can avoid the harmful contamination by the moisture, chemical or even dust. Along with that, it can increases the mechanical strength of the fiber. The mechanical strength means, so if the fiber strand which can be installed by the time because of some kind of stress by the fiber, that can be taken by this polyethylene jacket or polyurethane jacket. So in the next slide we will discuss about what is the principle of carrying of light by the fiber. Of course, the main principle of the light guided through a fiber is multiple total internal reflection. In order to understand this multiple total internal reflection, what is the total internal reflection, that we should concentrate, and later we can understand how the fiber which can carry the light through an optical fiber. The first thing is, in order to understand total internal reflection, I shall consider the two regions of refractive index, that is N1 and N2. N1 is called as higher refractive index region, which is something like a core medium, and N2 is another region of refractive index, that is it's similar to the cladding. And core and cladding are the two regions of refractive index n1 and n2, which is separated by a particular boundary called as x dash. X dash is the region which is in between the core and cladding, called as interfacial region. Interfacial region are the boundary region of the two different refractive index material. A dotted line which indicates that the normal. Based on the reference of this normal, we can understand how the total internal reflection that will taken place through a certain angle. So here the two regions of refractive index are there. X dash is interface of n1 and n2. Interface means the both are having the common boundary, something like the common wall in between the two houses, something like that. The x dash is interface region. n1 and n2 are the two refractive index regions. n1 is whose refractive index of n1 is slightly greater than n2. So you can take n1 as a core, n2 as a cladding. The separation region is x dash. Whenever the light which incident to the interface region with certain angle with respect to the normal. See, this is the light which is initially from higher refractive index region to the lower refractive index. So whenever the light which is come from denser medium to the rarer medium, because the refractive index of the region is more, means it will be act as a denser medium. The refractive index, low refractive index, means it will be act as rarer medium. If the light is enter from denser medium to rarer medium, that can bends away from the normal. See, with respect to this normal, this is the normal. With respect to this normal, a certain angle, the light which incident at a interface region, this is the interface. X dash is interface between n1 and n2 at certain angle. This is the angle made by the incident ray, that is C is a ray that incident at a point O by certain angle. Then the ray, it is simply refracted into the second medium, so that is n2. So denser to rarer. So you can see the angle of refraction. This is the angle of refraction. You can see the angle of incidence is less than angle of refraction. This type of phenomena called the rarer denser to rarer medium, the light bends away from the normal. That means refraction angle is more than that of incident angle. So because of denser to rarer medium. So then if you increase the ray of incidence in the first region, I will take an angle, I will take a ray which is greater than the initial one, that is C is a initial ray which is simply refracted into the second medium. What happens? The ray A is incident at a point O with certain angle whose angle is equals to theta C. Theta C means critical angle of incidence. By the time here the bends away from the normal, that will taken place. By the time if the ray is increases in the incident medium, that means in the denser medium, that ray which is just grazes through an interface, that means here the angle of incidence is increased. Obviously the angle of refraction is going to be increases one certain angle, that ray which is going to refract through an interface, that is A dash. C dash is the refracted ray of C and A dash is the refracted ray is of A. So by the time the refraction angle becomes 90 degree, by the time whatever the angle of incidence in the first medium, that will be called as critical angle. I will define what is critical angle in the next slide. Next is, if any ray, that means B, whose angle of incidence is greater than theta C, theta c, that is simply reflected back into the same medium, that is b is the ray of incidence whose angle is greater than theta c, that ray which is simply reflected back into the same medium, that is b dash. B dash is the refracted ray whenever an angle of incidence is greater than theta c. So you can see that we took the certain angle, that refraction angle becomes the refracted ray which is transmitted through a medium 2, and if you increase the angle, by the time the refracted ray is also increases an angle which is just grazes through an interface, that particular angle of incidence is called as theta c. By the time the angle of refraction becomes 90 degree, if any ray whose angle of incidence is greater than theta c, that ray which is completely reflected back into the same medium. So hence any ray of incidence whose angle is greater than critical angle, that reflected completely back into the same medium. So what is theta c? Theta c is the critical angle. Critical angle is defined as the angle of incidence by the time the refraction angle becomes 90 degree. That particular angle is called as critical angle. If any angle of incidence whose angle is greater than critical angle, that ray which is confirmed for total internal reflection. This type of reflection called as total internal reflection. Next is, what is total internal reflection? Whenever the light travels from denser to rarer medium at an angle of incidence greater than critical angle, that is theta c. Theta c is the critical angle. The ray is not refracted, but it is reflected back into the same denser medium. This phenomena is called total internal reflection. We make it underline. If any ray which travel from denser to rarer medium whose angle of incidence at an interface is greater than critical angle, without any refraction, the ray completely reflected back into the same medium. This type of phenomena called as total internal reflection. Then what is the importance of total internal reflection? This is the very important point we need to understand. Because of this importance only, we are going to use an optical fiber. And the first importance is, so absolutely no optical power lost due to the absorption. You can see that this kind of practical situation in any kind of reflecting surfaces. The reflecting surface, suppose if any light which fall on any reflecting surface, certain quantity of light radiation which get absorbed by the reflecting surface only. But in the case of total internal reflection, no power is absorbed by the reflecting surface. Completely the 100% power which is reflected back into the same medium. So what happens if the reflecting surface which absorbs the light, if little absorption takes place, the optical signal will not sustain in the fiber core, leads to loss of information. Suppose if one reflection absorbs certain quantity of radiation, so then the optical fiber will not supposed to carry the light over long distance, because in the optical fiber there are plenty of total internal reflection takes place throughout the fiber, and the light will be follows the total internal reflection. If a certain quantity of radiation which is absorbed by the radiation, means that power will not sustain in the fiber. So because of that only, the fiber which retains the power as it is without any loss. Because of total internal reflection, The optical fiber has capable to a, carry a light over a long distance, and hence it avoids the usage of repeaters. Because of that, so optical fiber doesn't require too many number of repeaters. So normally what happens in the ordinary communication, for example mobile communication, the towers are nothing but repeaters or something like boosting stations. Suppose if you go some distance far from a telephone user, from a any tower, what happens, you can see that there is a weak signals. In such a cases we can't get a clarity in the communication. Because of that only we need to install a, a towers for every 5 kilometer radius. In the case of optical fiber we doesn't require such kind of boosting station called as repeaters, because the optical fiber which carry the light without any disturbance. The ray is propagated through an optical fiber, satisfies TIR at each point of incidence. This will continues till the other end where it received, and reconvert through the photodiode, the mechanism as shown in the figure. I will take the importance. Next is Snell's law of refraction. What is Snell's law? Snell's law is one of the law of refraction, according to which the n1 sin theta 1, here theta 1 stands for angle of incidence, theta 2 stands for angle of refraction, n1 stands for the refractive index of the first region called as denser medium, n2 is the refractive index of rarer medium called as cladding. n1 stands for denser medium refractive index, n2 stands for rarer medium refractive index. As per that, if an angle of incidence, that means the condition for total interreflection, the angle of incidence is equals to theta c, by the time the angle of refraction becomes 90 degree. That means when theta 1 is equals to theta c, that means theta 2 becomes 90 degree. That means the refraction angle is 90 degree, means the ray which is just grazes through an interface in the boundary region, that ray will be passes. By the time n1 sin theta c is equals to n2 sin 90, sin 90 is equals to 1, then n1 sin theta c is equals to n2. If you simplify that, we will get an equation, that is theta c is equals to sin inverse of n2 by n1. This is the angle of critical angle. Then what is the definition for the critical angle? Critical angle is the angle at which the refracted ray is just grazes through an interface. This type of mechanism that will be taken place whenever it undergoes a critical angle. So next is we will look into the numerical aperture and angle of acceptance. Numerical aperture is the condition, angle of acceptance is a condition of gathering of light through an optical fiber. The first is, you can see this will be a figure, cylindrical region, it will be called as a core, and the dotted line which is at the center of this cylinder called as axis of fiber. This is a core and this is an axis of fiber, and the core is surrounded by the cladding. I have not shown the cladding in this particular figure. I took the core itself for defining the numerical aperture and angle of acceptance, because the light guided by the fiber through that will be passed through core only. That's why I took core to define the numerical aperture and angle of acceptance. What is angle of acceptance? Angle of acceptance is, before that I will quote the numerical aperture. Numerical aperture is defined as sine of angle of maximum angle of acceptance, sign of maximum angle of acceptance. What is the importance? And it measures the amount of light that can allowed by the fiber for the transmission. How much the light will be carried by the fiber, that will be decided by the numerical aperture. For a good fiber, the numerical aperture is around 0.13 to 0.5 only. This will be the permitted value for the numerical aperture. If it is more than that, that kind of a fiber will not be used for fiber communication. If a fiber is having the low value of numerical aperture, whose value is less than 0.13, this is the permitted value, whose value is less than 0.13, that will not be used for fiber communication. Whose value is greater than 0.5, that will not be used for the fiber communication. But the range of the numerical aperture is value is from 0.13 to 0.5. This will be the permission. Once again I will define. Numerical aperture is sign of a maximum angle of acceptance. It measures the amount of light gathering capacity of fiber for the transmission. Acceptance angle is the maximum external critical angle made by the ray with fiber axis, then it refracted through the interface. See, if a light which is enters to a fiber from the source of light means any kind of LEDs or lasers, which enters to a fiber, that will be refracted into the fiber, that will be refracted through an interface. So this is an angle. If any ray which enters other than this angle, that means which is greater than this angle, that ray which is simply escaped out of the fiber, if the angle of incidence, this is an angle of incidence externally with this fiber axis is act as a normal. This is the surrounding medium, and this will be the denser medium. This is an angle of incidence, that is theta c. So if an angle of incidence is theta c, if you rotate around the fiber axis, we will get a cone. This cone is known as acceptance cone. This forms the virtually a cone. So through this definition we come across, if any ray, for example, if any ray which enters to a fiber within this cone is act like a funnel. We need to feed a fluid through a nozzle. That funnel, if any liquid which fill through a funnel, that will be confirmed for the filling of vessel. Otherwise, if any liquid which is poured out of this funnel, that will be wasted. Simply like that, here also this cone is act as a funnel for the fiber core. If light is enters to this particular cone, that will be accepted by the fiber. If any light which enters from this particular direction, that will not allowed by the fiber for carrying. Hence, if you rotate around the fiber axis with an angle theta c which forms the cone, that cone is known as acceptance cone. So whose angle is, this is, for example, from ear to ear the angle is theta c, ear to theta naught, ear to ear the angle is theta naught. Then the total angle of acceptance is 2 theta naught. 2 theta naught is an external acceptance cone angle. Theta naught is the acceptance angle. The ray acceptance cone angle, that is 2 theta naught. The ray rotated around the fiber axis with acceptance angle, which forms a virtual cone called as acceptance cone. Its angle is 2 theta. Then this 2 theta is acceptance cone angle. If there is a condition for carrying of light, that condition is if the ray enters the fiber core within the acceptance angle that geometrically confirms the TIR inside the fiber. Any ray enters the fiber other than this particular angle which fails to undergo total internal reflection inside the fiber. See, inside the fiber, if the ray if the ray enters to a fiber within the acceptance cone angle, that ray which is confirmed the TIR, otherwise that ray which is emerges out of the fiber. This will be the basic principle which is going to be used in the optical fiber. In the next video we will discuss about what is the expression for numerical aperture and angle of acceptance. Thank you.